Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, there will be two more examples related to basis for vector space. And for the first example here, we have set B, which consists of, this is the first vector, this is the second vector. You can see clearly that it is separated by comma, and this is the third vector. And you are asked to show that this set here is a basis for the vector space, where the vector space here is defined as polynomial of degree 2. And we all know that a polynomial of degree 2 has a general construction such as a0 plus a1x plus a2x squared. Okay, so in order to show that set B here is a basis for this particular vector space, what you need to do is you need to show that two conditions are fulfilled. So to be a basis, the first condition is B spans this vector space, and the second condition is B is linearly independent. So these are the two conditions. So to start off, we are going to consider showing the first part, which is we need to check whether B spans the vector space given here. So is it, okay? And our starting point would be, first we need to transform this part here into a vector notation, and that would be having C1 multiplied with, so for this one here, the vector notation is 1 for the constant, 1 for x, and 0 for x squared. Okay, so that is the first part, plus C2 for the second vector. Here we have 0 for constant, 1 for x, and also 1 for x squared. And the third vector is 1 for constant, 0 for x, and 1 for x squared. And the results of this, so this is the linear combination of all those vectors. The results of it is equal to something. We don't know what that is, so we're just going to let it equal to x, y, and z. So remember, our objective is to try and find the values for C1, C2, and C3. And in order to do that, we are going to turn the whole thing here into an augmented matrix. So we combine all the values. Okay, so here we have 1, 1, 0, 0, 1, 1, 1, 0, 1, and here is x, y, and z. So clearly, the next reasonable step that I can do is I can switch the position of row 3 and row 2. So therefore, row 3 switch with row 2, and we have the following result. 0, 1, 1, z, 1, 1, 0, y. Okay, the next part is, I think I would like to turn this value into 0. So therefore, that involves the following operation. R3 plus negative 1 R1, and that becomes 1, 0, 1 x 0, 1, 1 z. So 1 minus 1 is 0, 1 minus 0 is 1, 0 plus 1, so it's 1. So, sorry, 0 plus 1, 0, 0 plus negative 1, so this is negative 1, yeah? And here we have, hang on, let me check once again, 0, negative 1, so negative 1, okay. So here on this part here, we have y minus x. So here is y minus x. Okay. Next, what I can do is I can consider letting this value becomes 0. So here we have R3 plus negative 1 R2, and the result will be 1, 0, 1. This is X. 0, 1, 1. Z. 0, so 1 minus 1 is 0, negative 1 minus 1 is negative 2. Y minus X minus Z. So here we have Y minus X minus Z. Okay, so that is the result. Next, what I can do is I can consider this to be equal to 1. So I'm going to turn this number here into the value of 1. So I need to multiply negative 1 over 2 with the third row, and so the result here is going to be 1, 0, 1 X 0, 1, 1 Z, and here it will be 0, 0, 1, and here we have Y minus X minus Z over negative 2. Okay, so here is the final look of our augmented matrix, the simplest form, and we can see that here is, if you refer to this last part here, so that means C3 is equal to Y minus X minus Z over negative 2, which can be written as X plus Z minus Y over 2. Okay, so that's the answer for C1. So that is the value, the value of C3, yeah. Next, if you refer to this part, it says C2 plus C3 is equal to Z. Therefore, C2 is Z minus C3. And this is Z minus, so C3 is the whole thing here. X plus Z minus Y over 2. And that can be simplified as, well, here will be 2Z. So 2Z minus Z will be Z. So here negative X, so this is negative X, negative Y, positive Y. So this is the answer for the value of C2, Z minus X plus Y over 2. Okay. And then this one here refers to having C1 plus C3 is equal to X. C1 is X minus C3, so X minus X plus Z minus Y over 2. And if you simplify that, well, here will be 2x over 2, so 2x minus x will be x. Then here will be negative Z and positive Y over 2. So that's the answer for the value of C1. Okay, so based on that, we can write our linear combination as such. So therefore, what we have here is x minus z plus y over 2, and the first vector is 1, 1, 0 plus C2 is z minus x plus y over 2. The second vector is 0, 1, 1 plus C3 is x plus z minus y over 2. And the third vector is 1, 0, 1, and this is equal to x, y, z. And since we are able to write all the vectors as a linear combination, therefore we can conclude that, so based on the result, we can say that set B here spans the vector space of polynomial degree or polynomial of degree 2. Okay, so that's it. We are done with the first part. Next, we move on to showing the second part. which is we are interested to show that B is linearly independent. Okay, so question here is B linearly independent? And the starting point for this is to come up with a linear combination such that we have C1 and the first vector is 1 1 0 plus C2, second vector is 0 1 1 plus C3, third vector is 1 0 1, and instead of having xyz here, we will have 0 vector on the right hand side of this equation. So our objective is to find what is the value of C1, C2, and C3. So again, we can consider having it in terms of augmented matrix. We have these values. And if you try and do this process, try and apply the elementary row operations, you will basically practically doing the similar steps given here, except that all this part on xyz here will be 0. So basically you are just repeating the same step. Okay, so we can do that. So we can repeat the whole thing if you want. So here we have first R3 change to R2. Okay, so we have 1 0 1 0. And then 0 1 1 0 1 1 0 0. Next, what we can have is again we can turning this into 0, so therefore we have the process of R3 plus -1 R1, and you will have the result as such. The same result actually, you know, it's the same result as you have seen in the previous part. Okay, so we have, this is just 0 0 1 -1, this is also 0. And then if you do this again, for example, you want to turn this into 0, so the process here will be R3 plus -1 R2, and the result that you get here is going to be 1 0 1 x, sorry 0, okay, and then 0 1 1, this is 0 0 0 -2, this is 0, and if you multiply the third row with -1 over 2, so you will get 1 0 1 0 0 1 1 0 0 0 1, this is 0. So clearly from this you will be able to see that the value of C3 is 0. For this one is C2 plus C3 is 0, C2 negative C3, which is also 0. Yeah. For this one is C1 plus C3 is equal to 0, C1 negative C3, C1 is also 0. So you get this what we call the trivial solution. And notice that all the steps given here are exactly similar to what you have done right here, except that you just, you know, substitute the value of x, y, z with zeros. Okay. Because of that, since we get the trivial solution, what we can do, what we can say is that since C1, C2, C3 is equal to 0, therefore B is linearly independent. Also, since condition 1 and condition 2 are fulfilled, so again, what is condition 1? Condition 1 is related to demonstrating B spans the vector space, and condition 2 related to showing that B is linearly independent. So these two conditions are fulfilled, therefore we can say that B is a basis for vector space P2. Okay, right. Okay, let's move on to this example here. Hang on, I need to go and get my plug. I need to plug my laptop here. Hang on. Okay, right. So this example here is similar to what you have seen just now. And you can see here we have set X, and in that particular set there are three vectors. So here is the first vector, the second vector, and the third vector. And similarly, we have a vector space defined as polynomial of degree 2, where you can imagine the general representation would be a0 plus a1x plus a2x squared. Okay, so the first step is, of course, to demonstrate that x spans P2. So the question is x spans P2. So this is what we need to do first. And the starting point for showing that would be to consider the linear combination of all these three vectors. So we have C1, and this one here can be written in a vector notation. So that would be, for position constant, it will be 1. For position x, it is -1. For x squared, there is no x squared, so it is 0. Okay. Next, the second vector is this guy over here. So for constant, the value is 2. For x, there is no x, so 0. For x squared, it is -3. And for the third one here, we have value 0 for constant, 1 for x, and 2 for x squared. And those here lead to having results that can be represented as x, y, and z. So again, the objective here is to see whether we can find values for C1, C2, and C3. So in order to solve this, we need to consider the augmented matrix. So here we have 1, -1, 0, 2, 0, -3, 0, 1, 2. Okay, here we have x, y, and z. And based on that, well, what I need to do next is I can consider switching the third row and the second row. So that is what I'm going to do. So here I have 1, 2, 0, x, 0, -3, 2, z, -1, 0, 1, y. And I think what I'm going to do next is I'm going to consider changing this part into 0. So I will change the third row with this operation, +1, 1. And the result here becomes 1, 2, 0, x, 0, -3, 2, z. So here -1 plus 1, 0, 0 plus 2 is 2, 1 plus 0 is 1. And then we have, well, y plus x. Okay, right. Next is I'm going to turn this part here into +1. So I will multiply the second row with -1 over 3. And the result that I will get is 1, 2, 0, x. So here is 0. This is 1. This is -2 over 3. And this will be -z over 3. 0 to 1, y plus x. Okay, next is I shall consider having this value equal to 0. So the process that I need to consider here is R3, well, so plus negative 2 R2, okay, and the result that I shall get is 1, 2, 0, x 0, 1, negative 2 over 3, negative z over 3, and for this part here I shall get 0, so 2 minus 2 is 0, 1 plus 4 over 3, so that will be 7 over 3. And at this right hand side here, I shall have y plus x. So this is y plus x, and then I shall have negative 2 times negative z over 3, which means positive 2z over 3. Okay, and next what I can consider is I will turn this into the value of 1, and therefore I need to multiply 3 over 7 with the third row. So the result that I shall get is as such: 0, 1, negative 2 over 3, negative z over 3, 0, 0, so this one will become 1. So y plus x, so 3 over 7 y plus x plus, so if 3 over 7 times is 1, so we have 3 over 7 2z over 3, which you can see that this can be cancelled out. Okay, so based on that, we can then consider the solution of it. So here we have C3 is equal to 3 over 7y plus 3 over 7x plus 2 over 7z. So that is the solution for C3. Next is, if you consider this part here, you will have C1 minus 2 over 3, sorry, not C1, C2 minus 2 over 3, C3 is equal to negative z over 3. So C2 is negative z over 3 plus 2 over 3. So what is C3? I'm just going to substitute the result straight away. So here is C3, 3 over 7y plus 3 over 7x plus 2 over 7z. Well, then it becomes negative z over 3 plus 2 over 7y, so 3 and 3 can be cancelled out. Then plus, again 3 and 3 can be cancelled out, so 2 over 7x. This one will be 4 over 21z. Okay, and this can be simplified. Well, 4 over 21z and negative z over 3 can be combined and simplified, and it becomes negative 1 over 7z plus 2 over 7y plus 2 over 7x. So that is the solution for C2. Okay, and finally, if you consider the last part here, we have C1 plus 2, C2 is equal to x, so C1 is x minus 2, C2. So x minus 2C2, which is equal to x minus 2. C2 is, well, negative 1 over 7z plus 2 over 7y plus 2 over 7x. And that becomes x plus 2 over 7z minus 4 over 7y and minus 4 over 7x. Okay, so here we shall have so x 7 minus 4, so that is so hang on, let me check whether I made mistakes or what. I think it looks all right. Okay, so here we have 7 over 7 minus 4 over 7, so that will be 3 over 7x, and then we shall have 2 over 7z minus 4 over 7y. So that is the solution for C1. Okay. Okay, right. Therefore, what we can do is we can then write it in terms of the proper linear combination. So here, therefore, here we have C1, so 3 over 7x, 3 over 7x plus 2 over 7z minus 4 over 7y. And this is the first vector, which is 1, negative 1, 0, and then plus so here we have negative 1 over 7z plus 2 over 7y plus 2 over 7x, and the second vector is 2, 0, negative 3, and plus 3 over 7, hang on, oops, so here we have 3 over 7 y plus 3 over 7x plus 2 over 7z, and the third vector is, well, 0, 1, and 2, and the result here is equal to x, y, and z. Since we are able to express all the vectors here in terms of a linear combination, we can conclude that set x here, we can conclude that this particular set x here spans vector space of polynomial degree 2. Okay. Next is we need to show that is B linearly independent, and I think if we consider so for example let's consider the situation where we have C1 1, negative 1, 0 plus C2 2, 0, negative 3 plus C3 0, 1, 2, where this is equal to x, y, z, and I'm going to call this equation 1. So if we consider this part, and we have already shown that the solution for it, and we also consider its solutions, where C1 here is equal to this thing, so 3 over 7x plus 2 over 7z, hang on, 3 over 7x plus 2 over 7z minus 4 over 7y. C2 is equal to negative 1 over 7z plus 2 over 7y plus 2 over 7x. And finally, C3 is 3 over 7y plus 3 over 7x plus 2 over 7z. So this is what we can consider. We consider this equation here and the solutions provided. Next, if we let x equals to 0, y equals to 0, and z equals to 0, then equation 1 becomes something like this. C1 1 negative 1 0 plus C2 2 0 negative 3 plus C3 0 1 2 0 0 0, which is the starting point if you like to demonstrate whether the vectors here is linearly independent or otherwise. So therefore, subsequently, if we let x, y, z equals to 0, subsequently, the solutions for C1, C2, and C3 will be C3 will be C1 is 3 over 7 times 0 plus 2 over 7 times 0 minus 4 over 7 times 0, which is equal to 0. C2 will be negative 1 over 7, 0 plus 2 over 7, 0 plus 2 over 7, 0, and this is equal to 0 as well. And the solution for C3 is 3 over 7 times 0 plus 3 over 7 times 0 plus 2 over 7 times 0, which is equal to 0. And since I'm running out of space, I'm just going to give a statement of what's the meaning of all this. So this is clearly a trivial solution. So we get everything 0. And because of that, we can say that B is linearly independent. And since we have managed to fulfill this condition and also this condition here, therefore we can conclude that this particular set here, set X, is a basis for the vector space here, where the vector space is defined as polynomial of degree 2. Okay, I think that's all for now. Thank you very much for watching.